I'm going to look at a couple of problems where we get to use polynomials in applications and see how we use things like the factor and remainder theorems in these problems. So we have a first problem here with a rectangular box, and I'll let you read that while I make a diagram. So what's happening in this box is that these corner pieces are being cut out. We've got a dimension of x by x, and we know that the overall length of material is 15 and the overall width is 12. So I'm able to form some relationships for length, width, and height, which you could take a moment and try writing and then check my work. The length will be 15 minus 2 cutouts. The width will be 12 minus 2 cutouts, and the height is formed by the cutout being flipped up. Now, the volume of a rectangular prism is length, width, height. It's going to be a function model now, since everything's based on the cutout of x. So I'm going to make what is a cubic polynomial. Now, furthermore, we're told that this equals 162. So we're going to expand the left side, gather all the terms, and gather the constant term over to the left side. And when we do that, you can check your work, or check my work rather, on this to see that I get this cubic polynomial. So the factors of 162, this is where divisibility comes in handy. 2 is even, so it's going to 162 is even rather, so it's going to divide by 2. If I add digits, that shows me it'll divide by 3 and 9. The fact that it divides by 2 and 3 means it'll divide by 6, and so on. So I'm going to be able to say factors of 1, 2, 3, not 4, but 6, not 8, but I can keep going like that. I've also got rational roots that are possible. 1 over 2, 1 over 3, and so on. So working with these and trying them out, we will find that f of 3 produces this result with 3 substituted. And if you use a calculator and look at the results of that, you'll find out that it's 0. So x minus 3 is a factor, but I'd like to see if there are 2 other factors to this cubic. So I'm going to do synthetic division now. I'm going to detach coefficients, and I'm going to line them all up and make sure I have them all there. I'll perform synthetic division. You can pause this and try to do it yourself and see that you get the same answer. You should be doing that routinely, I hope. The 0 remainder confirms that I do have a factor. I'm going to write the quotient of 4x squared minus 42x plus 54, which, pardon me, has a factor of 2. So let's remove that and make life a little simpler. And that's going to be 27. Now, that trinomial inside, I'm going to get rid of the 2 by performing that trick that we've learned in the past for factoring, which allows me to divide by the 2 and multiply by the 2 on the other term to try to get the arranged pattern that makes factoring easier. And I'm going to get minus 3 minus 18, and I will redivide by 2 to bring it back into balance and simplify, leading to these other 2 factors. So what I've found out then is that the volume as a function of x can be written as x minus 3, 2x minus 3, and x minus 9, leading to zeros of 3, 3 halves, and 9. Now, I'm going to reject 9 because remember that x was the cutout size, and if I had a cutout of 9, I get no width, and for that matter, no length to the box anymore. But both 3 and 3 halves are permitted, so what this means is that x equals 3 or x equals 3 halves cutouts produce 2 possible boxes that meet the volume requirements. So there's one problem solved. Let's look at something related but also different. Okay, this problem, I have a right triangle and I have a description of the sides. So it'd be good to pause at this point and try to fill in the diagram and see if you can get the information together and formulas for this. Okay, what I've done is I've called this dimension b and this dimension height, base height. It's a Pythagorean triangle. Sorry for that. And the hypotenuse is one longer, so I went with b plus 1. Pythagorean theorem is used and simplified to solve for h based on b. Area is half base times height, so I've substituted the known area as well as the description of h that uses b. So now I've got an equation with a radical. I'm going to square both sides to remove the radical. So that's b squared 2b plus 1. And lastly, I'm going to expand to get the cubic term, a quadratic term, and a constant term. So again, we end up with a polynomial that's cubic, and we're trying to work out its factors. So, factors of 144. Well, we've always got plus or minus 1. We've got plus or minus 2 here. In this case, we've got plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8. Gosh, we've got lots of things. We've also got some rational roots because of that 2 in front of b cubed. And there's even more. So, a little experimentation. We'll find out, yes, this takes time, but f of 4 gives 0. So x minus 4 is a factor. So I should use b to keep my variables consistent. b minus 4 is a factor. So I'm going to use negative 4 with synthetic division, detach the coefficients, 2, 1, 0, and negative 144. We're missing the b term, but we've got to account for it. And doing the synthetic division leads to the result with a 0 remainder, which is what I expect. So I've got 2b squared, 9b, and 36. Now, that number 36 is positive and large, which is making me suspicious of whether or not there's even a way to factor this. What I'm going to do is I'm going to use the discriminant from quadratics, the b squared minus 4ac, which is going to be 9 squared minus 4 times 2 times 36. And what I'll find out is that's less than 0. So this produces no roots or factors or x-intercepts. So the only value for b that's possible is 4. Therefore h, you'll remember, was 2b plus 1 rooted, is 3. And the hypotenuse is 1 more than b, or 5. So that's the solution to that problem. In each of these problems, when you're doing applied polynomials, a real key is going to be making a diagram, assigning variables, getting a relationship between the variables. Often there's more than one equation, like in this case, Pythagorean theorem plus area, and then isolating one thing so that we get one variable. In the earlier case, we had length, width, height, and we're using volume formulas, substituting into the length and the width and the height to arrive at a polynomial formula. Once you've got your polynomial, you set it to 0, use factor theorem properties to try to find a factor, then synthetic division to break it down further. That's the basics of how to work applied problems in polynomials.